So where are we going modern-wise? I keep, with this whole notion of a shared memory, we struggled a little bit with either the Snoopy caches to deal with it, but we knew there was a bottleneck. Here's what a modern multi-core looks like. This is a 64-core machine. You can go out and buy them. There's a company called Tylera that was actually founded by one of the MIT profs here. And you can sort of notice that there isn't really a shared bus here. These guys basically just talk to their neighbors. You can send messages to the edge here, please, and there's a whole bunch of, memory arrays that hook off to the edge here. But if this processor wants a memory value, it sort of has to communicate with the edge and says, get me this information from memory. Typically a whole block of words, which can then be routed back and put in that processor's cache. So think of this as not so much as processors with some communication. This is processors with communication. So this chip is really all about the communication message, communication channels. And in fact, it's really the communication things that where all the architecture went, all the architectural design went, and figuring out how to do all this sort of message-based communication with the peripherals and then with each other in the different cores. So you have to rewrite your programs. The advantage is that by and large you're getting away from sort of shared memory as doing semantics, and you're replacing that with explicit message passing, which these machines can do very, very well. So, for example, one of these 64 machines can actually do H.264 encoding for like 100 TV channels at a time, 100 independent TV channels at a time, right? And you say, well, if I had to take my one processor and write a program to do that, it'd be very complicated. I'd have to figure out, when it's like keeping 12 plates all spinning at the same time. Some plate over there would need attention. I'd have to go back and make sure I did a little bit more on channel 1 before the people viewing channel 1 ran out of bits to see. Here, you can sort of say, well, each one of these guys is working on a separate channel. And by and large, so long there's enough memory bandwidth, that can be made to work. Okay, so these big MIMD arrays are really what people are starting to buy. Intel had a project called Laramie, which they were trying to sell you an 80-core version of something like this. So people are, there's other than Tylera, I don't think there's people who are out there yet. Some of the big Cray machines, the big multiprocessor Cray machines, the Titan, for example, is 500,000 AMD cores all lashed together with these big communication channels. So, there's in supercomputers now. They'll probably be in your laptop in a couple years. It's part of the way we're going. Yes, sir?
I'm assuming the 700 megahertz and 2.3 gigahertz are what is the clock speed?
Yes.
What makes it be so low compared to
Do you see that number? That's the power dissipation, 250 watts, right? That means that if this thing is not basically water cooled, it melts, literally melts. It'll unsolder itself from the board, right? So these things get very, very hot. So the real limitation nowadays is just, we can only dissipate so much heat off of these chips, even with fancy cooling systems. And so these clock rates are almost all determined by how much power dissipation your cooling system will provide. All your Intel chips, they have different, they're forever adjusting their clock. They sit there and there's hardware that looks at the temperature of the chip and reduces the clock rate if the temperature gets too high. So they're actually, your 4-core chip, if you're running on all 4 cores, the clock rate is, half or 2/3 of what it is. If you're running on 1 core, they have this turbo boost. So they're willing to let 1 core run really fast if the other cores aren't doing anything, because you can use up some of the power dissipation that running fast is, because no one else is using that power dissipation. You can say, oh, I can run really fast, I'm going to get hot, but everybody else is cool. So the total power dissipation isn't outside the envelope. So anyway, so the power dissipation is what really has driven us to multiple cores. Trying to make 1 core run faster and faster and faster just turned out to be a losing game from a power point of view.